4.3, we'll discuss it. 4.4, we're going to discuss it. You flip it over, let's hope that yours has something on the back. Section 4.5, we'll discuss it. And if I get through this, chapter 4 is basically done. All on this handout. You guys appreciate this? I went through each section is very good. You condensed it down for you, so you know what's going on here. Okay? Now that said, I gotta make a little, give you a little reminder. I think that section 4.2 has to do with inverses, I think. As we do this before we jump into it. I'll let a student read for us here and see what's going on here. There we go. Part 1. Let's look at this. One-to-one functions. And put this word underneath. Inverse functions. And we're going to show that notation to indicate if they want an inverse. One-to-one function, along with try to find the inverse of a function. Now, number 1, I thought I better do this before we jump into the handout, and that is, yes, here we go. Can anyone tell me, based on last week, if I gave you this function, right there, nice little quadratic, and asked you to find its inverse? Anyone? I haven't seen you for a couple of days. Well, can anyone look at x squared plus 2 and tell me a little bit about it? Because I got to find its inverse. There's only 2 steps to find an inverse. To find the inverse is easy. But some functions do not have inverses. That's what we were talking about last week. Does this function have an inverse? If not, forget it, move on. Some functions do not have an inverse. Can anyone tell me what functions do have an inverse? They must be one-to-one. Now, let me give you a set to look at, and we'll get back to the question here. Suppose I gave you a set A, and inside this set, with your help, I will try to form some ordered pairs, just at random, replace x by randomly some numbers, do a calculation, and list a few ordered pairs. You start out with -2. If I try -2 and replace x by -2 and do my math, I think you end up with a 6. We'll try another number. -1. Replace x by -1, I think you end up with a 3. Let's try 0. 0 is easy, 2. Then out here, we'll try 2. I'll put a 2 in there, I get 6. And we'll close it up. Those are some ordered pairs, if I have no mistake in the math, belonging to that function. Is that true, guys?
Yeah.
I didn't make a mistake, those are ordered pairs. So what do those ordered pairs tell me? Should I take time to try to find the inverse of this function, or does it not have one? It doesn't have one. Why? The 6's repeat, the y's repeat. You can't have that to happen. That's the whole thing about saying it's 1-to-1. So guys, you got -2 paired up with 6. You cannot pair something else up with 6. It's got to be by the description, 1-to-1. Now, your textbook, the author of the textbook, he was on campus not too long ago, and we all met him. He and his son do the textbooks for you guys for MATH2, pre-calculus. And we asked, this is what he does for you, which is nice. In your textbook, when you do your homework, he tells you in the directions right above there, this is a 1-to-1 function. In other words, you know it has an inverse. He doesn't ask you to sit there and think about, like I just asked on this one. He doesn't do that. He just goes in and just gives you a function that's guaranteed to have an inverse to begin with. And he tells you the directions. This is a 1-to-1 function, which guarantees you you got an answer. This one though has no answer. Those in the textbook will have. Set that up like that. So guys, I do not have an inverse on this one. There's no inverse. No inverse on this. Now though, number 2. I think if I'm ready for the handout now. Oh, I am. Okay, I got f of x is equal to, here goes, 2x subtract 3 from your handout over x plus 4. Now, did I, as the author of your textbook, did I at the top there say this function is 1-to-1? At the very top, it does say the given function is 1-to-1. Therefore, you know it has an inverse. You don't have to worry about that x squared business. And I want you to find the inverse. There's only 2 steps to find the inverse. Step 1, does anyone recall anything at all about what it would mean to find the inverse if this should have worked with those ordered pairs? What was that discussion when we had a discussion about the inverses? What did that mean to do? Interchange. So you're going to interchange the coordinates. Put it right here. That's all it comes down to. This coordinates. And you know what coordinates are? They're x and y. So in other words, if this should have worked, this ordered pair would now flip into 3, -1. Here, 2, 0. The x and the y interchange. If it should have worked. Now, this one I'm saying will work. I did not list ordered pairs for you though on this one. So can anyone tell me in step 1, how could I show that I want to interchange the x and the y on this function? What should I do? I have no numbers to work with.
Change denominator.
Do it again.
Change denominator with numerator.
Something else. Switch the x and the y, interchange them. You said, Professor, I have no numbers. If you gave me this, I could turn them around, make it 3, -1. If you gave it to me, Professor, I could change this to 2, 0. Why you didn't give me numbers, Professor? No, I didn't, but you can still do this. This represents the y, now make it the x. Equals, and make the x's y's. I'm just going to do it like this. There's step 1. There's only 2 steps. One more step. You interchange the x and y in the attempt to find what is known as the inverse. That's done. Step 2, after you interchange, now you solve for y. With that y by itself. Guys, you go back to this, where I interchanged, and solve for y. I would suggest you think of this x over 1, and do a quick cross multiplication. If you multiply in this direction, guys, we end up with xy plus 4x. Step back and look at it. In this direction, cross multiplication, 2y subtract 3. Yes or no? Now, can anyone tell me this crazy equation? The second step, the last step, to find the inverse is get the y by itself. And that will be the inverse. Does anyone have an idea how to get the y? Because I see a y here and a y here. And now wants to solve a y. Yes?
You put the y's on one side of the
Get the terms together that contain the y's. So let's leave xy where it is. And she wants me to move 2y over, Professor. It has a y in it. And everything else on the other side. Let's move that 4x over. So I got the terms together that contain the y. Now I wonder what she wants me to do now since I have the terms with the y. What might you do with them? Back that y out. You got x subtract 2. No problem. Still got this. Bring my work up here. And then divide. If we want to solve for y, divide both sides by x subtract 2. And guys, we'll end up with y's equal to, here goes, -3 subtract 4x over x minus 2. Right here. These cancel for us. Now you got the y by itself. Agreed? Now, if I made no mistake, watch the signs here, I'm not jumping the board here. Are we okay so far? If this is correct, this is, and we'll use this symbol, this is that function's inverse. This function, where is it? This function's inverse is that. After I interchange and solve for y. Only two steps, interchange, solve for y, interchange, solve for y. Now let's think about what that means though. Can anyone tell me right quickly, I didn't ask for it. Can anyone tell me right quickly, do it in blue here, an ordered pair that's guaranteed to belong to this function, the original function? I gave you some up here for this one. Can anyone look at 2x subtract 3 over x plus 4 and give me one ordered pair that is guaranteed to belong to that function? Think it for me. Replace x at random by a number and tell me what comes out. So we'll give you something.
1 and 1 over 6.
Okay, if I place a 1 in there, here we go. If I place a 1 in there, you're gonna get what? Negative 1 on top. Over what? 2 or 6 or 2 or 5? Yeah, I think it's 5. Was it negative 5? Help me out. Replaced by 1? Yeah, of course, it's gonna be what? Negative 1 over 5. Is that true? We're doing arithmetic. Now, was it negative here 2, subtract 3, right? Negative 1 over, and I think she gave me a 1, didn't she? 1 plus 4 is 5. Is it negative 1/5? Is that what you guys are saying? Like that? Okay, you say that? I'll accept it. Now give me another one. There's an infinite number of them. Let me list a few for you. If I replace x by 0, I thought someone would try 0 first. I think you get negative 3/4. At random, try maybe a negative number. Try a negative 2. If I replace x by a negative 2, not mess up here, I think you end up with negative 7. Watch my math here. Over 2. Yes or no? And I can list these all day. Yeah, I said, Randy, you've got 3 of them listed. What are you going to do with them? I'm going to now interchange the coordinates. They talk about an inverse. So we draw the red here. So beneath each one, let's turn them around. And I'm going to bring them over here. This now becomes negative 1/5. Rita gave me 1. Turned around, interchanged. This one interchanged for an inverse. Looks like this. And the last one we tried here was this. And there they are interchanged. Forming an inverse. Now what should happen? What should happen is, I may have made a mistake in the math. What should have happened, and we'll be very patient here, you'd have to say, Professor, you had better check to make sure you did not make a mistake here. Go back up here and replace x by negative 1/5 in the inverse. Here goes, guys. Here's my inverse. So negative 3, subtract 4 times negative 1/5, I'll put it right here, over negative 1/5, subtract 2. And crunch that out. In other words, do the math here. Let me do it fairly quickly. Negative 3, I think this turns into a positive 4/5. Denominator, let's go and use a common denominator there. 5, that would be a negative 11 over 5. Someone check me out, make sure it is. I think we have negative 11 over 5, okay, down there. Let's use a common denominator on top. I see a negative 15 plus 4. What's that? A negative 11 over 5. There we go. I guess so. Over a negative 11 over 5. I made no mistake. That's what he said. number over itself, is that one? Is that what we got here? Take a little time to get it, but it does check. This one, we don't have time to check all these. Let me try, look, we got fractions here, no problem. Let's try -3/4. We'll go back to my function, inverse, and replace that x with a -3/4. This one might be a little bit easier. And down here, -3/4, subtract 2. Clean this up. I see on top here -3, it's going to turn into a plus. 4's cancel, or 3. And down here, whatever it is, common denominator of 4, be a -11/4, I think. No matter what it is, I've got 0 over it. Is that 0? Were we expecting a 0? So when you flip these around, they will check. Now, go, that question mark. How many of these in the red? I tried 3. How many of these in the red that came from the one in the black? How many of these in the black and turned into red, inverse? How many of these can I list? Infinite. So you're gonna sit there, rest of your life and test, and test, and test, and test, and test? It's infinite. You perform an infinite number of work here. If you don't have the time, you're not gonna be able to do that. So there's a quicker way to check to see whether or not you have the correct inverse without going through, make sure it checks with numbers here. Just like Philip said, there's an infinite number of ordered pairs here. Guys, for check, we do this. We take the function and form a composite with its inverse. With respect to x. We're going to form a composite. I talked about composites last week. Some of us may remember what's supposed to happen. When I actually put, in this case it says, put the inverse into the original function. That's what this means, f of the inverse. Guys, here goes, we'll do it right here. The inverse, we think, is this strange number, or strange expression. This over this. We think that's the inverse. Right here. Is that true, guys? And we're taking f of this. Now, can anyone, before I crunch that madness out, if we have the correct inverse, what should come out for an answer when I finally finish it up? X, 1x. If it does not come out to be an x, I've got a mistake somewhere back on earth, back here. I have a mistake. Let's hope I do not have a mistake. I got to move on to other things here. Guys, find this, it will take a little effort. You go back to the original function and be patient. And here it is, 2 times. I'm going to be patient. Put the inverse in there. Get all this finished up here. Close this up. Come back to the original function. Subtract 3. All over back in the original function. X plus 4. There goes. Put the inverse in. Like that. And plus 4. Now, I've got some clever students in class. I could be clever at times. There's no way, though, you're a professor, even you're a professor. If I was just walking down the hall and you said, "Professor, simplify this for me." That looks nothing like it's going to simplify into just x. In fact, it's a little scary right now. If it does not simplify into x, we've got a mistake. You've got to go back and say, "Oh, I've got a mistake here. This is not the inverse." Guys, here goes. We've got to clean this up. Now, here we go. We're going to clean this up. First, we'll think this is 2 over 1. Let me do a little distributive property. -6 subtract 8x out front over x subtract 2. On the end, at 3, I need a common denominator. Guys, that's like 3 over 1. Let's put a common denominator of x subtract 2 in there on that last term, which is needed. like that. And now I've got this, be very careful, -3 times this, all over this. I'm gonna go down here, I cleaned up a little bit here, hoping for the best. I got the blue, and let's think of this 4 as 4 over 1. I need a common denominator there, I need 4, let's rewrite it. It's still 4, but that's my common denominator. This one looks like at this point, -3 subtract 4x over x subtract 2 plus 4 times x subtract 2, look at this, over x subtract 2. Woo! I hope I don't make a mistake here. You're gonna keep in mind, all this must come out the x. Here it goes. Let's finish it up. Now you guys got -6 subtract 8x. You guys, since you see back there, watch. Right here, I think that's -3x plus 6. See if you guys agree. Is that -3x plus 6? All over my common denominator. There, I'll come back to it. Bottom part, oh geez. I got -3 subtract 4x. This is madness. Down here I got 4x subtract 8. Hope I did not make a mistake. All over that same common denominator. Woo! We're still hoping that mess is x. A simple answer, x. Guys, going back to the top, these two will cancel. These two will cancel. At this point, I have a -11x over x subtract 2. That's the top. Down here, I see these will cancel. That gives me a -11 over x subtract 2. Please tell me, is that x? With a little dancing, will those two eventually cancel? Will the 11 cancel? And I'm going to be left with x. Wow. Now you see one of these on the exam, which you will. As it goes through 4.2, we found the inverses. And then I ask you for a check. You say, Professor, please give me a simple function. Professor, don't give me a function like this. Let's show it to me. Please give me a simple function like 4x plus 2 and find its inverse. Yeah, we did a hard work here, guys. It came out to be x. Now, if we did it precisely, I'm not going to do this. Not only does it check with this like this, you're supposed to also check it in the other direction. In other words, this. Turn it around and go through that composite again, it's supposed to give me x again. I always ask my students just do it in one direction. You don't have time to do it in both, it's supposed to work in both though. I usually ask for something like this or this. It's one. I'm not asking you to do both. Guys, any concerns here? Now, I'm not finished with it. We'll make it a little bit easier here. Let me go back. Here's the original function. Here we think its inverse is this. They don't look alike. But we check, and that is its so-called inverse. Now, let me ask you, since I just did a rational function, what more skills is this a rational function? Anyone tell me where the vertical asymptote will be located on this original function? If I were to graph it, where's my vertical asymptote located? Vertical. You set that denominator equals 0. It's -4. Is that true? That's my vertical asymptote. Where's the horizontal? Where am I over here now? -4. Where's the horizontal on this one going to be located? No. How do you find it? If the degrees match up, the fastest way, by the way, the degrees here are 1 and section one, they do match up. So where should my horizontal be located? This coefficient, -4, over this coefficient, 1, and I'm gonna end up with a -4, which I think we said back here. So my horizontal asymptote, if I should graph this, is at -4. Vertical back here, -4, they switch. They interchange. Something else to point out, can someone look at this real quickly and tell me, on the original function, just out of curiosity, where is my x-intercept if I were to graph this? Someone tell me right quick, I'll write it as an ordered pair. I hear it, 3/2, 0. You solve this, that equals 0, solve it. You get 3/2, 0. That's my x-intercept here. Now that should become the y-intercept on this one, if everything's been interchanged. Let's try to find the y-intercept on the inverse. And you know how to find the y-intercept. You go back and say, Professor, I need to find on that inverse, and I replace x by 0, looks like that. Guys, if I go up here and replace all the x's by 0, please tell me, will I end up with this over this? Will these two cancel out if I replace x by 0? So I've got -3 over -2. And is that positive 3/2, or does that agree with what was given to me back here? Except they interchange. That's what an inverse does. They interchange everything. The vertical goes into the horizontal. X-intercept goes into the y-intercept. And everything's been interchanged. Guys, take a close look. I did a hard one here with you guys. This one, we did it. We interchanged. We found the inverse, which looks like this, and then we checked. Was there another one on that handout besides this one? Get it out of the way. Before I ask, more than likely I'll be closing down with that next one. Before I ask for that last example, I think there's one more here. If you can come in Friday and we're ready for the exam, and I have placed a function on there where you find its inverse. Look at this. That's what you'd be hoping for. Goodness gracious, Professor, don't give me one like you used to erase. That was madness. If I just could find the inverse of this, and I'll go and tell you, it's 1-to-1, so it has an inverse. He said, Professor, please give me one like this. Because when you interchange the coordinates, you're going to rewrite it right quickly like that. Is that true? Then solve for y. Are you kidding? To solve for y, divided by 3. This is the inverse. You use that notation. And you're done. Now, would you prefer Friday on your exam to have one that looks like that, to find the inverse for it? Isn't that cute? Now, am I going to do that? No. Can't do it. I'll be something a little bit more demanding, not too demanding, but more demanding, just a simple linear function. Rena, tell me what that last one in that section was. I think there's only one more, right?
Yeah, x squared plus 4.
X squared plus, hold on now, f of x.
F of x equals x squared plus 1.
Now, hold on. Before you tell me anything else. Geez. I thought we just said a few seconds ago that there is no inverse for a quadratic. It's not 1-to-1. Didn't I just do one with you guys? And we said, no, Professor, it's not 1-to-1. And I think I used ordered pairs. So, no. Now, before I ask anything else about it, you know and I know. Look what think of it. This would graph into a parabola vertically shifted up 4. I think everyone in class would agree, Professor, there's the graph of x squared plus 4. That's true? Now, if you can visualize the graph, and the graph of this one's easily visualized, another way to tell it's not 1-to-1 besides forming ordered pairs, like I did on mine earlier, there's a test called the horizontal line test. If you're able to pass a horizontal line on your graph, and it intersects more than once, and mine does. I have 2 intersection points. Then that quickly tells you if it intersects more than one point, it's not one-to-one. It's called a horizontal line test, not vertical line test, a horizontal line test. Guys, there will be no need for x squared plus 4 to be dealt with. Move on, just say no inverse, professor, move on. But I think I did on your handout something to this function. What did I do to it? Arena, did I do anything else to it? Oh, I left it x squared plus 4?
Yeah, and x.
Oh, yeah, I did something else to it. What was it?
X more than equal to 0.
Nah. Oh, my goodness. Are you kidding? You see the graph staring at you. But then I placed a restriction on the side there. Yeah, well, look at that graph. That's a graph. But consider only what part? Where x is greater than or equal to 0. That means do not consider this now. Please tell me. If that piece now is wiped off, which it is, by that constraint, restriction, now is that remaining piece one-to-one? Would it pass the horizontal line test? It'll pass the horizontal line anywhere you wish if there's a one-point intersection. Now this one does have an inverse with a restriction. If she had not given me the restriction, it was left out, you say no inverse, professor, move on. So let's find the inverse of this one, guys. Number 1, interchange. Let's make this x and y here. Just interchange x, y. Easy enough. Step 2, solve for y. Only 2 steps. Now this one you've got to be careful. To solve for y, just move that 4 over. Now can anyone suggest what I would do now to get y by itself?
Square root.
Square root. Here we go. And we think this is the inverse. I'll use that notation. This is acting as the inverse of this. We think. Okay, guys, look graph of square root x factorial real quick. On the same grid. Let me put in green. You know what this is. It's that square root graph horizontally shifted 4 to the right. Almost like a transformation. Okay, let's go 4 to the right. Point some time here. And please tell me, based on your knowledge of a square root graph that we've done before, does the graph look something like that? Yes or no? So there in green is the inverse. There in the black is the original function with its constraint placed on it. There's a relationship between the 2 graphs. Anyone think they see a relationship between these 2 graphs? Now I'm throwing it out there. Maybe some students have seen this before somewhere. Maybe they know, Professor, I see a relationship between this black and the green graphs.
They both are shift and they are on first person.
Oh, hang on one second. This one is horizontally shifted, and this one is what? Vertically shifted. For it. Did they interchange there? One's horizontally shifted, the other one's vertically shifted. That's one thing, yes, that's one thing to take notice of. Oh, by the way, the x-intercept on the green one is what, 4, 0? Does that turn into the y-intercept on the other one? 0, 4. Is that true? So then you can interchange something else that you might not just grasp it. You might not see it at first. Yes?
Reflected across, the origin of like the line that goes through.
Wait, hold on a second. So you're telling me if I should draw a line, diagonal line, through the origin like this, that maybe, it's not wrong to scale, that maybe this reflected across that line may give me this. Or the green reflected across that line may give me this one. She's saying there might be a reflection from one to the other across that diagonal line, not across the x-axis, not across the y-axis that we've seen before, but across the line, y is equal to x. Straight line going through the origin with a slope of 1. Always happens. You grab a function with its inverse. We'll see that reflection. Now, here we go. If I accept this, let's go back to the blue. Here's the original function. We're going further. The domain on the original function arena, I gave you the domain. This is a set of x's. So the domain on the blue, here we go, is 0 through infinity. Set. The range on the blue, I graphed it in black guys. The range up here, someone tell me what the range is on the graph of that x squared plus 4, the up and down. What's the range on that little piece right here? Is it 4 through infinity? Now let's go to the green. This is its domain and range. Anyone tell me what the domain on the green, which is acting as an inverse, what's the domain on that? Okay, I get 4, make it 4 through what? Infinity. What's the range, the up and down, on the green one? It drops down to a 0, and it rises forever. Yes or no? If I look at the two graphs. Now take a look at the domain of the range. The domain of the range is blue, which I graphed in black, is this. The domain of the range on its inverse to green is this. What happened? You compare the domain of the range on the original function and the domain of the range on the inverse, what happened? They interchange. Did one become the other? It always happens if you're dealing with an inverse. And the statement here for us, the domain of an inverse is equivalent to the range of the original. The range of the inverse, right, like this, is equivalent to the domain of the original. These statements. Are we okay? Now, to close this down, I need to check. We'll close this down. Check to make sure we do have the inverse correctly. Let's form the composite with respect to x, and we had better get x. If not, that in the green, where was it? Got the blue here, up here. That may be the wrong inverse. Down here it is. Guys, this means take f of the inverse. And we're hoping to get x. Right here. The inverse we think is, we're hoping to square root x subtract 4. Is that in there? I'm taking f of that. Now, can someone tell me what f of that means? What am I supposed to do at this point? Go back to the original function, which was up here. Replace x by that, square root x subtract 4. I think it says to square it back there. And then what? Add 4. You square that, you end up with x subtract 4, square root drops off, plus 4. 4's cancel. Oh my goodness. It checks. Is that true? Now, Arena, was that the last one on that section 4.2? Done. So you got to make sure you understand how to find an inverse, the domain and range of the inverse, how to check an inverse. Whew, I even went through and graphed it for you. Okay, let me step back and look at it, but we did quite much. Even step back here, looks pretty good. That black graph and the green graph, looks like there's a reflection, one to the other, across that line. Y is x. Any concerns here, guys? Anything at all? Okay, now, part two. Enough of that done before break. Part two, Marina, you're close by. Tell me what part two is concerning. Yes, we'll get this, enough of this done. And there's a section 4.3, guys, in your textbook. We'll call this part one again. Exponential function. By the way, that word exponential, I see this word. Functions. Just left rational functions. Inverse functions, everything has function attached to it. Now, exponential. Did I give a definition, a brief definition, or did I say something about it? Read that to you.
It's just the formula, f of x equals a and ax
Raised to the x?
raised,
That's the way it looks.
and a more than zero.
Oh, they put some restrictions. A must be positive. Okay, tell me more.
A is gonna equal one.
But you take something and raise it to a power. And then put some restrictions on that base. That's my base there. Base A has the restrictions, is it, Professor? This base must be positive. Greater than zero. And please don't let it be one. Wonder why they say don't let it be one. Why would they place a restriction and say, please don't let this down to the base be one when you raise it to that power of x? Why?
Because it's linear.
Tell me again.
It's like a linear.
Oh, something else, easier than that. Yeah.
It always end up being one.
That's always one. One raised to any power is one. So trivial, it says don't do that. Leave that out. One raised to any power is one. Exactly. Now, I don't know whether I had some examples on that, Rita, did I?
Yes,
Did I have some sketches to do or not?
yes.
Like what?
F of x equal to x.
Hang on now. Okay, so number one, f of x is equal to, this is called an exponential function. Looks like this. She wants me to sketch this. Now, since this is my first one, I don't mind if you guys form a table. I know it looks elementary. I'll try that many points. Let's just form a table right now and plot points for the table and see what this shape looks like. Is the shape of parabola? No. Is the shape of a square root graph you saw earlier? No. Let's see what the shape is. I'll replace my -2, guys. It looks like this. 2 raised to a -2, and I'll come back to it. -1, 2 raised to a -1, 2 raised to the 0, 2 raised to the first, 2 squared. And you can create other numbers if you wish. 2 raised to a -2, we all know is 1/4. Here's 1/2. Anything raised to a 0 should be a 1. This is a 2. This is a 4. I'm gonna plot those points, see what shape of an exponential may look like. And then see what else that section has for us. Guys, if I plot those I have there, those, are you ready for it? Out to here. Now, -2 up 1/4. -2 up 1/4, let me give a reference there, 1, barely above, right there, barely above the x-axis. -1 is a little higher, so that's 1/2. 0 is up to 1. 1 is up to 2. Put that here. And 2 is all the way up to 4. Like that. Guys, connect those, not a straight line, not a parabola, not a circle. Please tell me, based on what you see here, might it look something like this? You guys agree? You have to take that shape. How's that? Yes or no? Now, you guys who are leaving the classroom at certain times, I hope you have a good reason, because I don't allow that. I hope you have a good solid reason, it's distraction. Do we agree with this, guys? So that's the graph of 2 raised to the x. Now let's get the domain out of the way since we have the graph in front of you. The domain on this blue graph is open. And the range on this graph, can anyone describe the range, the up and down? How far down does that blue graph drop? Dropping towards what? Towards the x-axis, which is 0. How high up does it go? Goes to the so there's the domain, the range on the exponent. Yeah.
Why is it bracket 0?
Right here. Hang on. Right here. Now, look at it. That's a key point about the exponential. Does it actually touch the x-axis? Out here, does it actually touch the x-axis, or does it just get close to it? Tell me right here. Oh, so right here. Professor. That's what I want to hear. Should that be open? Does it ever touch the x-axis? It never touches the x-axis. So the range, the up and down, is up close to 0. In truth, isn't it? Domain, all real numbers. I tried these for myself. You tried anything. And that's the graph of an exponential. Now, was there something else on there to graph besides that?
G of x
Okay, g of x, hang on, see if we can get this out of the way. G of x equals what?
equals 1/2 x
1/2 raised to the x.
raised.
Okay. Now, I know why I placed that on there. We'll get this and then take a break. I'm going to do a table again. By the way, does that fit the description for an exponential? Let's go back and see the restraints here, constraints. The a, the base, must be positive. Well, my base is 1/2, it's positive. And the a, the base, cannot be 1. No, mine's 1/2. So this is an exponential function. What does it look like? I'm going to do it quickly. I'm going to wrap it on the same grid. Because I want an observation before we take a break. Guys, we'll try the same numbers. Try different numbers yourself on the table. -2 would be, in this case, 1/2 raised to a -2. Here, 1/2 raised to a -1. 1/2 raised to the 0. 1/2 raised to the first. 1/2 squared. First one, I hope we all know that's 4. 1/2 raised to a -2. Does anyone know what 1/2 raised to a -1 is?
No, it's 2.
Is it 2? Of course, this one's 1, this is 1/2, this is 1/4. Wow. Let's close down for the break. I had it blue, let's hope the red holds up for me, and we'll plot these points. Out -2, up 4. Well, -2, up 4 on this graph up here. -1, up 2. Here. 0, 1, oh, they share a point. Out 1, up 1/2. And finally out 2, barely above the x-axis, 1/4. And that's 1/2 raised to the x from that table. Guys, connect these. We stand right here if I can. Get these connected. And on down. Close to the x-axis, does not touch it, as Phil told us earlier. And there's the graph of, in red, 1/2 raised to the x. The blue, y is equal to 2 raised to the x. Now before we take a break, does anyone see something going on there between those two graphs?
With some.
So hang on. Are they inverses of one another? Or if they are, then we discover something else. I don't think they are. Hang on just a second. On the side here, Karina, here's the original function. You want to find its inverse, hang on, these two steps. You interchange. Step one, and then step two, you're supposed to solve for y. Now, I'm trying it on this first, since you mentioned. Does anyone think they know after step one, after you interchange, does anyone see anything at all to do to solve for y? On 2 raised to the y, how are you going to solve for y? Not 2 plus y, 2 raised to the y. Anyone think they know how to solve it? I don't think so right now. There is a way, but not for us yet. Something else I'm looking for, based on that graph. What is it? Before we take a break. You see the red graph, you see the blue graph. Do they have a relationship?
Reflecting over the y-axis.
Exactly. There's one, if you reflect one across the y-axis, you get the other one. So if I reflect, let's say, the blue, this piece here, from here to here, across the y-axis, it's now here on the red. If I take this piece of the blue and reflect it across the y-axis, it now becomes this piece. So it's a reflection of one to the other across the y-axis. Wow. And that's what an exponential function does. Now, guys, I told you before we start today, we're going to be busy, extremely busy. We've been busy already. Was there more in that section 4.2 to do before I leave it?
4.3.
4.3.
Yeah, there's one.
One more? One more to graph or what?
Sketch.
Oh, sketching. Okay, we're going to have to hold off until after the break. Now I've got to talk to Mr. Parker. He's going to help me out after the break. Guys, any concerns here? At this point? Is the class getting a little tougher as we move along? It is. Now I'm really getting into the good stuff for pre-cal. To get you ready for Math 7. So it's going to take off like crazy here soon. Okay, guys, take your, let's see what the time is. 2 after you'll be back. Got your 15-minute break. I'll get your test.